going to go ahead and continue our discussion on conservation of linear momentum. So from Newton's third law, we get that the mass 1, or m1, times acceleration 1, or the acceleration of the first mass, is equal to minus m2 times a2. Okay? From that, we can obtain m1 times dv dt is equal to minus m2 dv dt, 1 and 2. Sorry about that. Thus, we can also write this as dp, or d momentum of the first one, dt, is equal to minus dp2 dt. Okay? Or we can write them as dp1 dt plus dp2 dt equals 0. Okay? So this is the start of the conservation of linear momentum. Okay? So since the total combined momentum of two objects together never changes, we can say that that last equation can become this, dt, or d dt of the first momentum plus the second momentum is equal to 0. And then if we take the integral of that, we get that these two momentums added up is equal to some constant. Okay? And we can generalize this to any number of objects, or n objects. So basically, the addition of each momentum should all add up and equal to some constant. Okay, or we can say the summation from j equals 1 to n of p sub j is equal to a constant. Okay, so let's look at this pictorially. So before a collision, we have some total momentum of a system. We have p1, or the momentum of the first ball here, and then we have p2, the momentum of the second ball here. Okay, and after they collide, we have some p total again, and we'll have two different momentums here. We have some p1 and some p2. Okay, and these are different momentums now. Okay, so if we look at this, okay, our conservation laws in general, if a value of a physical quantity is constant in time, we say that that quantity is conserved. And so that's what we have here with momentum. Okay? And we have some requirements for momentum conservation. Okay? So first, the mass of the system must remain constant during the interaction. So basically, we have to have some closed system, and that system has to be the same mass the entire time. So we can't say that, if we're looking at billiards again, we can't say that one of the balls just left and it's gone now after the collision. Okay, and then there's no mass anymore, like it disappeared. No, we have to keep those two balls in the system. Okay? Also, the net external force on the system must be 0. Okay, so there's no external forces acting on that system, and there's just these internal forces going on, or the forces inside the system happening. Okay, and so the law of conservation of momentum is that the total momentum of a closed system is conserved. Again, that is the same equation that we just found in the previous one. We can also say something else about this. We can say that the initial momentum is then going to be equal to the final momentum. Okay? That's what this means by conserved. The total momentum does not change. Okay? It'll still have the same total momentum. So, we can also say that the final momentum minus the initial momentum is equal to 0. Okay? Alright, let me quickly talk about the meaning of a system. I keep saying it. is basically a collection of the objects in whose motion you are interested. Okay, so you are interested about the two billiard balls, so both of those combined is going to be your system. Okay, so here is an example as well. We have two masses here, or two cars, and so we're interested in that system. We're interested in what the interaction is, what is going on with the motion, the kinematics of it, of the two vehicles. So that will be your system. Okay, so my system before and after, we have a net force is equal to 0. We have some momentums, P1 and P2, and they equal some total P, right? Okay, and same thing with after. We'll have a different, a different momentum, but it'll still equal some total momentum. Okay, now we're going to go ahead and quickly draw out a problem-solving strategy for these problems. Okay, first identify a closed system. Remember that our total mass is constant, so it needs to be constant, and no external forces act on this system. Okay, write an expression representing the total momentum of the system before the event. So whatever the event may be, it might be an explosion, it might be a collision, whatever it may be. Write an expression representing the total momentum after that event. Okay, then we'll set these two equal to each other, and we'll solve the equation for the desired quantity. Okay, so that's why I put this in here. Back here, our initial is equal to our final momentums, since our momentum should remain the same. Okay, since momentum is conserved. So let's go ahead and do an example of this. This is example 9.6. It states 2 carts in a physics lab roll on a level track with negligible friction. And I'm going to go ahead and quickly talk about these carts. These are something you would definitely have seen if we were in class. These are close to frictionless air tracks. So kind of like the air hockey tables that you play like at an arcade or something. It pushes air so that these guys will stay very close to being frictionless. Okay. In this case, these carts have magnets on their ends so that when they collide, they'll stick together. Okay. So the first cart has a mass of 675 grams and is rolling at 0.75 meters per second to the right. So we're going to define this as positive x. Okay. So we'll say that this is M1. Okay. The second cart has a mass of 500 grams and is rolling at 1.33 meters per second, also to the right. Okay. Then it states after the collision, what is the velocity of the two joined carts? So we want to know the velocity in the end. One thing to note, that this one is moving faster than this one. So in order for them to collide, this first mass on the left side should be M2, right? Because it has to catch up to the other one. So we have M1 and M2 here now. Okay, so let's go ahead and follow our procedures. So first, we want to identify our closed system, and that will be the two objects. Okay, let's write an expression for the total momentum of the system before the event. Okay, so we'll say P before, or actually, why don't I just put initial? That makes more sense. Okay, say P initial. Okay, and this will be, we have two different masses, right? So we'll have the momentum of the first mass plus the momentum of the second mass. Okay? So this should be M1 V1 plus M2 V2. Okay? Our final, because that's our next step, is to write an expression for the total momentum after. We'll say P sub F is going to be now a different momentum. And if you notice, they stick together, right? So then they'll have one velocity of the two cards, right? They'll be moving together. So we're going to have some total mass. So whatever these are two together, times our final velocity of the pair. Okay? So this will be M1 plus M2 times our final velocity. Okay? And so we are looking for this final velocity. Okay. So now our last step is to set these two equal to each other and solve the equation for what we want. So we want to find this value here. Okay? So let's go ahead and do that. We're going to say P sub I is equal to P sub F. And we're going to say M1 V1 plus M2 V2 is equal to M1 plus M2 times V sub F. Okay? And then we can go ahead and solve. V sub F is equal to M1 V1 plus M2 V2 over M1 plus M2. Okay? Let me see if I have another page. I do not. I'm going to try to squeeze this in. Okay? So M1 is 675 grams, so that would be 0.675 kilograms. Okay? Times our velocity, 0.75 meters per second. And this is in the right direction, so I'm going to say that's positive x. So I hat plus my next one is 500 grams, so 0.5 kilograms, times the velocity, 1.33 meters per second, and it's also moving to the right, so I hat, divided by our total mass, so 0.675 kilograms plus 0.5 kilograms. Okay? So we can go ahead and plug all of that in. And note, I did change my my mass to kilograms. You could have left it the same since we do divide it out, but it is a good idea to always switch it over just in case. I think it's always a smart idea. Okay, so I've got my top and then 0.675 plus 0.5. So I get my final velocity is 0.997 meters per second, and it is in the I hat direction. Okay, so a couple things to note is that looking at this final velocity versus our initial velocities, and we want to make sure that it makes sense. Okay, so our M1 was traveling at 0.75 meters per second. Okay, then our M2 was traveling faster at 1.33. So we have something faster that hits something a little slower, and then combined they move at a velocity between the two. That does make sense if you think about this logically. Okay, so it's always good to do a little bit of a check in your head to make sure that things make sense. Okay, So we're going to go ahead and do another example in the next video.